So yeah, the idea of this talk is it's a kind of bridge because what you have seen just now, the talk about the Bethe-Salpeter in frequency space, and what you will see tomorrow when the business learning will discuss how to compute those optical properties via real-time propagation. So actually, Maurizio just discussed the derivation of the Bethe-Salpeter via the ID or via the Schwinger. Instead, I will focus on the real-time approach. And actually, I'm not going to discuss the equation of motion for the response function, but rather to focus really on the equation of motion for the density matrix and how to extract from the time-dependent density matrix the response function. So let me start from some basic concepts. So what we want to describe is the behavior of the electric field inside the material. So we know that inside the material we have the electric field and the polarization, and the two they are related to the what is called the electric displacement. And in general, when we apply the electric field, there is an induced polarization or a variation of the polarization, which can be expanded via some coefficients to first order, second order, etc. Now, so far we focused and also my lecture to the case of a small perturbation, so to the linear response regime, where the variation of the polarization is just related to the first order electric field via this tensor, which is called the polarizability. So in this equation in compact form is just delta P equal alpha V. Now we also know that the polarization of electric displacement and electric field can be related by, the electric displacement can be replaced by the dielectric function. So there is another relation between polarization and electric field. Then using these two equations, we can trivially relate the electric function, which is the quantity we want to compute, to this polarizability. And this is what we do in the frequency space, and it was the subject of the talk of Maurizio. But then we can also try to compute the electric function, if you want, let's say, without directly extracting the polarizability, but computing the change in the polarization and the change in the electric field. So these are two alternative approaches to get the same quantity. Now, what Maurizio discussed is this Bethe-Salpeter equation, which is here in compact form. And then from the Bethe-Salpeter equation, this L propagator, one can get this frequency-dependent polarizability, applying the dipoles, these are the dipole operators, to the four-body response function. And the nice thing of this approach is that this L can be constructed in terms of only equilibrium quantities, the Kohde-Sham wave functions and the Kohde-Sham energies enter in this L dot and then defines L. And then it's also useful to have this expression because one can analyze the pose, can get exactly the excitation energies, etc. However, one alternative approach, which is based on real-time spectroscopy, is, let's say, much more close to what is done experimentally. So the idea is that experimentally, you cannot directly test the response function. What you do, you have a material, you take a perturbation, usually an electric field, and then you measure the response of the field. And then from that, you extract the response of the function of the system. So how this can be done in practice in a numerical simulation, one has to choose a specific perturbation, again, the electric field, evolve some equation, and this will be the main subject of this presentation. And then from this equation, extract the time-dependent polarization. And then, as I said, we have polarization and electric field, we do the Fourier transform, and we can get the polarization. So if you want to do that in practice numerically, you start choosing your electric field, and it will be, let's say, a function of time. You can have a different shape, and it will have a polarization. So in practice, when you run simulations with the YAML, before actually running the simulation, you have to decide the electric field, check which symmetries are broken by the electric field in your crystal, and use this YPP, which is the YAML post-processing, or in this case, pre-processing tool, to remove the symmetries from the, let's say, the properties of the material. And then after you do that, you can do a real-time propagation. So in the YAML code, we have two versions of real-time propagation, which are called YAML-RT and YAML-NL. And they actually propagate two different equations. YAML-RT propagates an equation of motion for the density matrix, while YAML-NL propagates an equation of motion for the conditional functions. Here, these are just a sketch that I will discuss in details, and mostly I will discuss this equation of motion, while Mirta tomorrow will discuss what happens when you move to an equation of motion for the wave function. And then from this equation of motion, one can get the time-dependent polarization, and in practice, again, you use the YAML, YPP, RT, and then post-processing tool to Fourier transform this to get the spectrum. Okay, so these are just the general concepts. Now, let's dig a bit more in the mathematics. First of all, what you've seen so far, what is the philosophy of YAML, is that we want to combine DFTs, so to use the DFT starting point to do many-body perturbation theory calculations, or what we call ab initio many-body perturbation theory. So we always start from the DFT equation, and we get eigenfunctions and eigenvalues. At equilibrium, you compute your zero-order green function from these quantities, and then you do the grammatical stop, for example, to get the quadratic corrections we have seen that yesterday to get the meta data. Now, if you want to go out of equilibrium, you can apply the same philosophy. The only caveat is that the formalism for equilibrium doesn't hold anymore. So we discussed yesterday that in the equilibrium case, you have this switching, this kind of fake time, which is switching on of the interaction that you need to introduce diagrams. In the out of equilibrium regime, when you have a laser pulse, what you have to do is you have to change about the path on which this fake time is defined, and formally defined on this Kelvin contour. So we are not going to dig into the details, but just know that once you define this Kelvin contour, you can define the same kind of equation, the same Dyson equation that you have at equilibrium on the contour. Then the equation can be moved from this time on the contour to the real axis, to the real time, and you can extract the quantities from which you can get experiment. So the main outcome of this say analytic continuation from the Kelvin contour to the real axis is that in the end the Dyson equation becomes an equation of motion for this lesser field function. An equation of motion which contains the forthcoming token and then the condition integral. And one can from this equation of motion for G lesser derive an equation of motion for the one density matrix. So there is this relation between the two. And the equation of motion has this form. Now, in getting this equation, there is a key approximation which is called the generalized Kahneman-Weyl ansatz, which enables you to close the equation of motion because, in principle, this object is a function of G lesser dt prime, and now instead you want to reduce it to a function of. So this is the general framework, which is very powerful. And for this lecture, and in general for what we do in the YAML code, we do something which is much simpler. We neglect this collision integral, and the equation of motion takes this very simple form. So in the equation of motion, which in the end doesn't need the definition as I sketched, just the general equation of motion for the density matrix presence of the static Hamiltonian. Here it comes with the anti-Fock Hamiltonian from the equilibrium with power approach, but then one can replace the anti-Fock Hamiltonian, which the RT plus the screen exchange Hamiltonian, which is what we use in many body perturbation. Okay, so now we start from this equation with the RT plus screen exchange approximation, and I will try to dig a bit into the details of the physics which it contains and how it relates to the data. So first of all, so far the equation of motion was sketched without indexes, so I represent instead the indexes. So this one body density matrix depends on time, but also depends on some indexes of bias indexes M, N, and K. And these band indexes are obtained by taking the density matrix in real size and projecting it into the condition as a step. It's an equation of motion which evolves in time, so we need the starting point equals zero condition, and this is the condition. So an equilibrium, the density matrix is diagonal, and it just contains the equation of the states. In practice, if you have a material with a gap, you will have the valence states which are occupied, the conduction states which are empty, so this will be either 1 or 0. And then it has these commutators, these brackets represent the commutator. It means that what you have in between the square brackets should be represented in this space, this in the bottom index. So it's the sum of this intermediate index of the two operators projected in the condition system. What we put in the equation in the ab initio framework, so the equilibrium part will contain the band structure. So principal animal structure in practice, what we do is to put the GW structure. And then these two terms, which are the variation of the uplift, exchange relation, static self-energy, will contain the minimal terms. Plus the equation, there is explicitly the external field. So if you're familiar, for example, with my independent density function here, it is a rather linear equation. The main difference is that this static self-energy is no longer in space, so you have interaction at longer range, while the is a longer theory. And then the other comment is that in principle, starting from this, you can introduce also dynamical effects. If we plug back the equation, we not neglected. The density, we don't know in principle how to include the systematic dynamical effects. In this theory, we can go beyond this equation by putting back the collision integral, and in principle we can capture some dynamical effects. Now, explicitly, I will write down the form of this, that is 11 step by term. So the equilibrium Hamiltonian is just a diagonal term in the transition space, quasi-particle energies. The variation of the active potential is just the difference between art at equilibrium and art evaluated at the time dependent density. And then the exchange correlation self-energy, as we said, in principle we can take any static self-energy. In practice, we use the statically screened exchange self-energy. We can take the difference with respect to the equilibrium case. And in the compact form, we can sum the two together. There is this variation of art plus variation of the screened exchange. The variation of the screened exchange can also be written as just a statically screened W plus the variation of the density matrix. So let me also comment that when we propagate in the code the density matrix, we can also add this term, which is a kind of a very rough approximation in the collision integral. And this eta is a constant dephasing term that will make the oscillation of the density matrix go to zero in time. It can be a constant or it can be computed from the imaginary bound of energy. And this is the way in which in real time the dephasing enters, similar to in the frequency space, there is a dephasing also entering in the broad markets. So some remarks on the classical field. The variation of the active potential can be split into a macroscopic and into a microscopic part. So the macroscopic part is the average over the supercell. For example, if you take a 2D material, the average of the supercell goes to 0 and the supercell goes to infinity. So if you take the distance between these two layers to infinity. While the microscopic part contains a lot of things. However, if you are in a bulk, the macroscopic part is also important. Physical part is what gives this longitudinal transversal splitting. But it is also a nasty term because it is non-analytical in the density matrix. So what we do in practice is we remove the macroscopic part from the equation. So we we don't include the macroscopic part in the active potential, but we assume that the macroscopic induced field can be absorbed externally. So it means that the active potential will take this family part on top of it. It means that now it doesn't have the macroscopic part, so there is the bar also here. But then here we have the total field. And then, now that I have this bar self-energy, what I can do is I can expand this linear order in the density matrix. It has this shape, just a functional derivative of the variation. This expression is, in general, an approximation is exact for functions which are in the density matrix. And also, it provides a force connection with the Bethe-Salpeter. So this object, the functional derivative of sigma with respect to the density matrix is what is called the kernel of Bethe-Salpeter. Already seen. And in the code is something which is needed both to compute the Bethe-Salpeter, so you need to build this kernel, but also to do real-time propagation. You will see that you need to construct what I call the real-time conditions, which are again the same object. So let me dig a bit further in the expression of the kernel. So the kernel of the Bethe-Salpeter contains, we said, the variation of the active potential. The active potential is just the classical interaction, so this is the interaction pool of interaction due to the density of all the electrons. Here is represented in the Feynman diagrams, the density of, and one electron which is propagating is interacting with the density of the other electrons. Now, what I can do is to take this time-dependent density and express it in terms of the density matrix. And it just becomes like that. So now the density R prime becomes the sum of N1 and 2, the time-dependent density matrix, and the orbital R prime. And this is convenient because now I can take all this part and make it a D. And this is what is called the electron exchange interaction, is the variation of the active term times the density matrix. So this V, the interaction here, this is N1 and 3. And this is the density matrix, and then N1 and 3. And we can observe here that the electron which is propagating in momentum space will conserve the momentum via the interaction of the wave field. So the active term doesn't change the momentum of electrons. And then now that we have this compact expression, so V times the density matrix, we can take the variation and we get this expression. So this is an object which is static in time, and we take the flow of the exchange. Now we can also do the same for the R-delta screen exchange self-energy. And this term is expressed in this way, so it is the G0 real function and the W with the spin interaction statical screen, which comes from the LBA, was discussed yesterday. Again, this I can take at equal times, so it is G0 that is diagrammatic expression. And I can also, in this case, take this density and expand it in terms of the density matrix this time, in terms of the density matrix in the Cauchy band spectrum. So these are all and some orbitals, and now I end up with the density matrix times something which is the interaction projected in the transition space. So at variance with the antithermic, we have an electron propagating flow, which is the down interaction via the screen interaction. The momentum is changed from K to K minus Q and then back to K, the self-energy. So this term in the equation of motion carries some exchanging the momentum. And the functional derivative, if I express this in the compact notation, is just the variation of this with respect to the dependence. This goes away, and it's just the direct electron interaction, again static, statically speaking. Now to comment on this functional derivative, But the first one is that it's static, but the second one is that here we are assuming that this term is zero. And then in the linear response framework, the reason is that this term will lead to higher order terms in the W interaction. Also, in the real-time propagation, if we wanted to include somehow this term, we should consider an interaction which is time-dependent, and this would require the use of the collision integral that I was showing at the beginning. So if we are not including any collision integral, this term is in the real-time propagation. Okay, so I've provided in details all these terms of the equation of motion. Now let me show that this equation of motion also reduces the Benezet beta in the linear regime, so in the case of a small perturbation. So what I'm going to do now is assume that my perturbation is weak, and I expand all the terms that appear in the equation of motion to first order in the spectrum. So the density matrix, it has an equilibrium term plus a first order term. The equilibrium, as we said, is zero order condition plus variation. Then the commutator of the density matrix with the equilibrium Hamiltonian has the two terms, equilibrium plus the variation. The equilibrium term goes to zero because the Hamiltonian is diagonal and also the density matrix is diagonal, so it's zero. And then I just download this term. So if I want to write my equation of motion for the linear order, I have the change in the energy that types type the. The second term, the variation of the self energy, as we said, we expanded this using the Benezet kernel. So here, if I plug the equilibrium density matrix here, this is zero, the variation. So this term is already first order, so the commutator, and I get the first order. Then I have the commutator with the density matrix, but since this is first order, I just wanted the zero order term. And the zero order density matrix is just the occupations. So here I end up with the change of the occupations times the kernel times the density matrix. And so I put it here. So these two terms actually are the Benezet equation. So here it is the Benezet equation appears in that line with the subdetermined method. Let me write it in compact notation. So now I call it H bar. The one Hamiltonian, again, remember the bar, excluded the macroscopic induced arc term. And finally, the last term, which is the product field. I want to expand this to first order in the field. So I have to take this to first order and get equilibrium. The leading order is already given by the field. And this gives just this term. So the field times the change in the occupations. Now, since I have this change in the occupations, these are different from zero in the case N is in the conduction and M in the balance. So these general M indexes can be replaced by conduction and balance. And then in the end, I plug this in my equation of motion. I change all the index conduction and balance. And this is the real-time formula of the Benezet equation. Now, what I can also observe is that this equation of motion, this Hamiltonian can be diagonalized from conduction balance space and exciton space. And if I use the excitonic space, I can also rewrite this equation in terms projected in the excitonic space for the Lambda index. And here I see that basically this equation describes coherent oscillations of the matrix at the excitonic characteristic. With the leading order term take the equation. And basically one can expect that the density matrix for each lambda term and also the Now, let me talk again about the fixed bar and the connection with the response function. Now I propagate this equation, and then I take the variation of the density with respect to the total field. I get this chi-bar, so this number available processing. This is equivalent to propagating the equation of motion with the Coulomb component. So now also the macroscopic art included, and the external field just when I do the variation, the time I obtain the full response function instead of the bar response function. So these two are two different response functions, which can be used both to get the physical property. For convenience, one usually works with this chi-bar, but please keep in mind you're assuming there is the total field. So how am I doing this time? Okay. Closer to the end, so that was for the discussion of what the physics, which is contained in the equation of motion. So let me just do the final remarks. So we said that we have an external field, and that this external field gives some symmetry that we have take into account. For example, here this is the Boolean zone of a bulk silicon. So if I take the Boolean zone of bulk silicon in K-space, there are many points which are related by symmetry. Here, for example, there are highlighted these endpoints, the Boolean zone, which are all equivalent. Then when you do a simulation with quantum espresso will give you the wave function just at one of these 8 points, because all the other are related by symmetry. What is called the irreducible Brillouin zone will contain just L. But now if I apply a little field in some dimension, for example, connecting gamma and prime, then the response of this L point and L prime point will be different because the electric field is breaking this symmetry relation. So what is needed is that you expand the wave function of quantum espresso to construct these at both the K and the L and the prime point, and then to propagate both the equation of motion. This is what is done. So after you do that, you can perform the real-time propagation. As we said, we get the time-dependent polarization before we transform it. We can get the dielectric function. And what was shown in the first application of this scheme is that if you actually propagate the equation of motion without any anti-Planck exchange collections of energy, you will transform it, and you will exactly obtain what is called the independent particle absorption. So here is the comparison with the absorption computed at the RPA level, dependent particle, with the independent particle propagation at time for bottom electron. And you can really see now switching on the self-energy effects, and you see actually what we discussed, that the real-time propagation, like the anti-Planck exchange, will give the same results as the previous pattern, which in the case of formula is crucial to get the description of the explaining perspective. Also, some technical details of the implementation. So since we have to propagate an equation of motion, in practice what we do, we start from the density matrix effectively, we verify equals 0, and then we have to obtain the time step interval from t to t plus a time step dt. And this is obtained by this functional, which is starting from the equation of motion. So when you will propagate the equation of motion, there are different schemes for doing that. So the easiest scheme is what is called the Eulero time step propagation, where this F takes this form. But then in the code, you can also select other forms of the propagator, the exponential, which has this form, and the inversion, which is the implicit propagator, which has this form. And then you can also have a multi-step propagator, for example, where first you take the density propagated time t plus dt. Then you take this over time, in this case, t plus dt divided by 2. Then you take this and you use it to construct the function of the t plus dt divided by 2. You get this and you propagate again. So it's a step propagation. For example, there's the AON, which is again a two-step, but it's the function at time t and time t for plasticity. So the main message is that the real-time propagation is a tricky numerical procedure, and one has to pay attention to the size of the time step and the kind of propagator that you use. And then one last topic on what are called the gauges. We have to put the coupling with the external fit in the equation of motion, and the standard, I mean, there are different ways to do that. So one way is to use the so-called length gauge, electric field times polarization, which is this one, which is what is implemented in the YAML code. And then from propagating in this gauge, one can, for example, start the polarization of the procedure that I've shown. Be aware that there are other gauges, for example, the velocity gauge, where instead of E times P, you can have A, the vector potential times the current, J, which will take this form. And then one can also start the time-dependent current and try to construct optical properties or other quantities from A and J. So here you see that the velocity gauge, you have the velocity dipole, V, representing here also the current, and here you have the position dipoles, which are in that gauge. The two are related by this equation. However, an important remark is that the velocity dipoles can also be defined for the capacitance, and equal to M. These are defined while instead the position dipoles they are defined for this case. So in principle, the velocity gauge is more complete. In practice, however, it has issues with some rules and is very unstable. And this is why our code will prefer to stick with this approach. Now, we have seen before that to the leading order, this equation of motion reduces the equation of motion for C and D conduction and balance. And the conduction and balance dipoles are well defined. And this is why you can use this equation of motion for the linear response. If you want to go beyond the linear regime, you would need in general all the matrix elements and all the dipoles. And this means that this equation of motion cannot be used to go beyond the first order the external field. So if you want to go beyond first order, there are other techniques, and in particular, tomorrow, Mirta will discuss the time-dependent approach. And yeah, just one last remark that I'm done. So we have discussed in details how this equation of motion can be used to compute optical properties, but it contains much more because it's not just a linear equation. So what is called is a general equation, which works for arbitrary times, and in principle, one can think to use that for modeling pattern of experiments, just to think pattern group fields and with that, I got.